Good morning. Welcome to another wonderful day at Chautauqua. My name is Bob Spiritus. I coordinate these talks for the Science Group. Our president, Bob Hopper, is in the back. Teresa Cameraman Dr. Cameraman is monitoring the website and for the chat box. And somewhere else we have a few other people in the audience who are part of our group. We wanted to welcome you today to hear Dr. Robert Davidson talk about carbon. He's a PhD with chemical engineering degree from the University of Wisconsin-Madison. Oh, I have to talk louder? Is that better? Okay. Our speaker today is. Well, I have to move. I have to move my body closer.
Get your mouth close to the mic. That's what you have to do.
These scientifically oriented people always want to argue. What can I say? Okay. Is this better? Okay, our speaker today is Dr. Robert Davidson. He retired from 3M after a 36-year career developing processes to make unique materials found in cell phones, computer monitors, dental restoratives, electric transmission cables, rocket fuel, and many other products. He's going to talk to you today about carbon, the key element of human civilization. Please welcome Dr. Bob Davidson.
Good morning. Thank you for the opportunity to tell you about carbon, an amazing element that's had a profound effect on human civilization. A little later in my talk, I'm going to talk about coal. And how many of you have ever seen or touched coal? Oh, we're all old enough, we have. If I do this to a younger group, none of them have seen coal. But just in case you haven't, my wife is passing around some bags of coal. And please don't open them because it's black and it will get your fingers in your clothes and the pews and everything black. Let's see. Let me go back. You probably have all seen this graphic of the periodic table of the elements that lists all of the elements that we know about in the universe. The first 94 of them occur naturally here on Earth. Most of them occur only as compounds where two or more different kinds of elements are bonded together to make something. But a few of them, some of them, can be found here on Earth as pure elements. And of those, a few of those have been known to humans since antiquity, like gold and silver. And one of the earliest ones that's been known is carbon, which is element number 6. Carbon was known to ancient people as the soot that collected on the tops of their caves when they had a fire burning underneath, and as charcoal, which is a partially burned stick of wood. If wood is burned and there's not quite enough oxygen, it chars, a bunch of chemical reactions occur so that all of the other elements, or most of them, leave, and you're left with this piece of essentially pure carbon. And people about 28,000 years ago began using these sticks of charcoal as a communication tool. And they could draw beautiful pictures on the caves. And that started a very long time ago. But that was only the beginning of human reliance on carbon. Time went on. And about 8,000 years ago, charcoal became the basis for a process we now call smelting to get metals out of ore. And if you put a piece of ore in a wood fire, not much happens. But you can burn charcoal, and it burns at a much higher temperature than wood does, and it's hot enough that it causes a transformation in the ore to another form called an oxide. And charcoal also gives off carbon monoxide when it burns, which reacts with the oxide ore, and it liberates the pure metal. And so that happened about 8,000 years ago, and people gradually learned to do other various kinds of metals. The Bronze Age started about 5,300 years ago when people found out that not only could they get separate metals, they could put metals together, and if they got the right combination of copper and tin, you got a material we call bronze that was much, much stronger and tougher than any of the separate metals. And that began the Bronze Age with really high quality tools. And then time went on. and gradually people found that they could get iron out of iron ore, which was even stronger than bronze was. And most metal production today is still based on this process where you take a carbon compound like, well, now it's not charcoal, it's a carbon compound I'll talk about later, and it reacts with the ore, and you can get the metal back out of it. To fully appreciate what carbon can do, I have to give you a little bit of a chemistry lesson here. The basic building block of materials is the atom, and atoms consist of a nucleus that's made up of protons with a positive charge, neutrons with no charge at all, and so those are dense, they're in the middle, and then there's a sea of negatively charged electrons around it to balance the charge on the protons. But the electrons can't be just any place. They're not there randomly. The atom is set up like layers in an onion, and so it's got shells, and each shell can only hold a certain number of electrons. So the first shell can hold 2, the second shell can hold 8, the next shell can hold 8, and so forth all the way through all the elements in the periodic table. And the periodic table has this strange shape because it's set up based on the structure of the atom. The order of the elements is based on the number of protons in the nucleus. So hydrogen has 1, helium has 2, and you get to carbon that has 6. And the rows and the length of the rows are set up to correspond to the shell that has the outermost shell that has electrons in it for that element. So the first shell can hold 2, so you get hydrogen and helium. The next shell, you can add electrons into that one. So when you get to carbon, it's got 2 electrons in the first shell, and then it's got 4 electrons in the second shell, so it's half filled. And when atoms bond together, they do so using only the electrons in the outermost shell. So the periodic table tells you a lot about how elements can bond together. And it turns out that carbon is just perfect for bonding to other elements. It can bond in multiple ways. Carbon atoms can bond to another carbon atom. They can bond to a wide range of other elements. And they have the ability, they're just the right size to be able to share either one electron with another element, another atom, to form a single bond, like between carbon and hydrogen here. It can share 2 elements at a time from 2 atoms and make stronger double bonds, or 3 electrons at a time to make triple bonds. And carbon can make little molecules. It can make long chains. It can make branch chains like a tree. It can attach in rings of various sizes. This is 3, this is 7. Carbon can make some very special rings that are called aromatic rings. It forms a 6-member ring, but then each carbon atom in the ring contributes 1 more of its electrons that circulate around the ring, and it's shared by all 6 at once. That makes it a really stable compound. And carbon also can bond in a way that the molecules can be mirror images of one another, like your hands. They fit this way, but you can't superimpose them this way. And carbon can make all kinds of structures like that that are really important. Because carbon has this versatility, carbon is found in a very, very large number of compounds that exist. There's an organization called Chemical Abstract Services that maintains the global catalog of all of the compounds known. And when I checked last month, it had about 204 million substances in it, and carbon is in a very large fraction of all of those. Carbon occurs naturally here on Earth. I've mentioned 2 in the category of called pyrolysis products, the soot and the charcoal. And these pyrolysis means that they were formed in a fire. But you can get carbon compounds that are essentially pure carbon by digging them or getting them out of the earth. So I'm going to start by talking about some of these. And the two most opposite ones are diamonds and graphite. Diamonds have a structure where every carbon atom is bonded to 4 other carbon atoms, and this structure goes throughout the piece of diamond. Graphite, on the other hand, takes advantage of aromatic rings, and it's built of sheets of these rings attached to one another to make up a sheet, and then the sheets stack on top of one another to make a piece of graphite. And that gives them vastly different properties. Diamonds are colorless and transparent. Graphite is black and opaque. Diamonds are the hardest naturally occurring mineral, and graphite is really soft. So diamonds are used as the ultimate abrasive to cut through and grind away things. Graphite, on the other hand, has the property that these sheets can slide over one another, and it's oftentimes used as a lubricant. Diamonds are an electrical insulator, whereas graphite is a conductor. You can pass electricity through it quite nicely. Diamonds are, on the other hand, a really good conductor of heat, and graphite is good, but not nearly as good as diamonds. When I say diamond, you probably think of gemstones, and they're very rare. Well, it turns out that diamonds themselves are not rare at all. And there's a lot of diamonds that are mined. There have also been ways developed to make synthetic diamonds. And most of the mined diamonds and the synthetic ones are used for industrial purposes to take advantage of diamond's property of being very strong, very hard, and you can make great cutting tools out of it. So you can take small industrial diamonds, embed them in a metal tool, and you can cut through. They use it to drill wells into the ground and cut really tough metals and do all kinds of very difficult cutting and grinding operations and polishing operations. Most of the synthetic diamonds are small, and they have imperfections in them so that they're colored and not quite perfect, so that's why they don't end up as gemstones. But people have figured out how to make gem-quality synthetic diamonds, and you can go to the jewelry store today, and you can buy rings that have a synthetic diamond in it, and they're virtually the same price as the natural ones, only they are absolutely perfect. So all in all, between the mining and the synthetic diamonds, diamonds aren't rare. There's about 1.8 million pounds of them made or dug up every year. Graphite also can be obtained from the earth. It can be obtained in big pieces and crystals, but they're uncommon. And so most graphite is found as tiny little flakes in with some kind of rock. But people would like to have big pieces of graphite, so they figured out ways to take the tiny little pieces of carbon at various ways of getting it, and put it through a process that can form it into a larger shape, and then heat it to a very high temperature to recrystallize it as a piece of graphite. And so you can get very large pieces of graphite these days. And the graphite, you're most familiar with the use of graphite as pencil lead. It takes advantage of the property that it's really soft, the layers slide off of one another, and it's the next communication tool based on carbon after taking charcoal, which artists still use to make great pictures. The big graphite pieces are formed into electrodes for arc furnaces and arc lights. Graphite pieces, even before people knew how to make really big ones, became the key piece of making electric motors, because you've got this spinning part of the motor and you have to get electricity to it. And if you just put a wire against it, the wire and the rotating piece wear each other out pretty quickly. But if you put a piece of graphite in between, you can put electricity through the graphite's lubricating, it rubs on the rotating armature, and they don't wear away very fast, and you can get power to the rotating part of a motor. And there's other uses of graphite as well. Now, people have wondered for a very long time, why is graphite slippery, And they figured out that it's in layers, and then they wondered, how small is a single layer? What would it be like? And in the 1960s, a scientist used an instrument called an electron microscope to get an image of a single layer of what makes up graphite, and he called it graphene. And so they could get an image of this on a piece of graphite. But it took until 2004 for two scientists to figure out a way to isolate a single sheet of graphene. And they did it using Scotch tape. And I used to work for 3M. I'm very happy with Scotch tape. So they took a piece of graphite and they polished the surface. And then they put Scotch tape on it and they peeled it off. So they got, some layers stuck together on the Scotch tape. They took another piece and stuck it on that and ripped them apart. So now they had some layers on one part, some layers on the other part. And they did this over and over and over again till they managed to get one single sheet of graphene stuck to a piece of Scotch tape. And that was enough that they could do measurements to start characterizing what graphene really is. And what they found is and they won the Nobel Prize for doing this. So what they found is that graphene has just amazing electrical, magnetic, and quantum mechanical properties because it's only one atom thick. So quantum mechanics is a part of physics that we don't often think about because it doesn't often pertain to us, but it's part of what makes the GPS work on your phone and lots of other things. So quantum mechanics is important. And they found that it's extremely strong, stronger than diamonds, but it's a tiny little sheet. And they say, well, what can we make out of it? But to do that, you need more than one sheet stuck on a piece of Scotch tape. So people have figured out ways to separate the graphene layers from graphite and do it in a way that suspends them in a liquid and keeps them from sticking back together. Or they can heat certain carbon sources and get a cloud of carbon atoms and get it to deposit on a surface as a graphene sheet. So now we can get more of it. So people are trying to figure out what is it really good for? And the answer so far is mainly for using its special electronic properties. So it's experimentally in, maybe you can buy them now, used in displays and solar cells and LEDs. It's also beginning to be put into materials like tennis rackets as a reinforcing material. And some people are even experimenting with it in concrete as a reinforcing material that also seems to reject water entry and make better concrete. Now, if you have a sheet of graphene, you say, well, what happens if I roll it up? Well, nobody's figured out how to roll up a sheet of graphene, but people have figured out how to make tubes that have a wall that's made up of graphene-like material that's one atom thick, and it's got pretty much the same structure as graphene. And depending on how it's made, you can get different kinds of electrical properties from it. And these two are very strong and very stiff. So carbon nanotubes are more available than graphene, but they're still not all that common. And so they've been used as additives to reinforce things. Again, sports is an early adopter of lots of high-tech materials, so you can get tennis rackets that are reinforced with carbon nanotubes. And there's a new use that's being developed where you can make scaffolds out of the carbon nanotubes. And they're compatible with living cells, so they've put bone cells into the scaffolds and found ways to grow them, so they're beginning to be able to grow replacement bone parts. And we'll see what the future brings in replacement parts that use graphene or carbon nanotubes to begin. It's also been found that you can get other shapes that are single thickness surfaces of carbon. And these are, when you get them as spheres, they're called fullerenes. The name is based on the fact that an architect named Buckminster Fuller developed the geodesic dome, and these shapes are sort of the same arrangement as geodesic domes, and they come as spheres of various sizes. People are still trying to figure out what to do with them. Now, there's another man-made kind of essentially pure carbon called carbon fibers. And these have been around for much longer than the ones I've talked about so far. They were first made in the late 1800s as the filaments in early light bulbs, because they are pure carbon, they are in the graphite structure so that they conduct electricity, they can withstand really high temperatures, and so it was a good start at an electric bulb, a filament for an incandescent light bulb. But by the people could only make them in little short pieces, just big enough to put in a light bulb. But gradually they learned to make longer pieces, and now you can get continuous threads of carbon fiber that are literally miles and miles long. And although a short piece is very stiff, if it's so thin, this is a photomicrograph, a picture through a microscope showing a carbon fiber, and this one's a human hair. So they're so thin that as long as you don't bend them too sharply, they are flexible. And so you can weave them into fabric. And when you have fabric like that, you can impregnate it with various kinds of resins that you can cure and plastics, and you can make carbon fiber reinforced materials. So they're tiny, tiny versions of the rebars that's in concrete. And because they are so strong, they're actually stronger on a weight and size basis than steel is. You can make parts for helicopters, automobiles. These are used a lot in tennis rackets and golf clubs, bicycle frames. And if you've ever flown in a Boeing 787, the fuselage is all made out of carbon fiber reinforced plastic. So it's very strong, it's very reliable. You don't have to worry about falling out of the sky if you're in one of these planes. Now, so carbon can make a very wide range of materials that are just fully carbon. Other atoms can occur in pure form in a few forms. For example, oxygen, if you bond two oxygens together, you get the oxygen in the air that we breathe. If you bond three oxygen atoms together, you get ozone, which is a problem in smog, but we rely on it in a layer of the atmosphere to shield out the ultraviolet rays. Otherwise, we all have skin cancer, suntan lotion or not. But carbon is known to make over 500 different structures that are fully carbon, which is just amazing. So the carbon materials I've talked about so far have well-defined structures, but there's another class of carbon structures called amorphous. And amorphous means that they don't fall in a reproducible, reliable structure. So this is a schematic of a part of a piece of coal. And so it's got rings, it's got chains, it's got some other atoms in it like oxygen and nitrogen, but it's nearly all carbon. And if you took two samples, no two samples of an amorphous material are going to be identical. They vary somehow. So now I'm going to talk about some of these materials. I mentioned soot that just collects, on things like the surface of the cave. People have learned to burn things in a way that makes a very special kind of soot called carbon black. And carbon black consists of tiny little carbon spheres that are bonded together in aggregated chains. And it's essentially pure carbon, and it's because of carbon black that you can get a nice smooth ride as you drive down the street. because it's carbon black that makes your tires black because it's the material that reinforces the rubber to make the tire. The first rubber tires were just rubber tires. They were white, and they erased themselves against the street in no time at all. So this was a really big breakthrough in automotives. Carbon black is also the pigment used in inks and paints and plastics to make things black. A very special kind of charcoal is called activated carbon. And it's made by taking things and heating them the way you'd make charcoal, except you do it a second step to it. And in the second step, often done at a higher temperature than the first step, you let in a controlled amount of oxygen or steam into the hot charcoal piece itself. And that causes chemical reactions that cause the development of pores, tiny little tunnels throughout the piece. And you can take, if you do this right, you can make a piece of activated carbon that changes the surface area of the piece from 2 to 5 square meters, a square meter is about a square yard, per gram of material, to as much as 3,000 square meters of internal surface area in a gram of material. So that's like half the area of a football field is inside these tiny little tunnels in the activated carbon. And lots of molecules like to stick inside these pores. And so they're used a lot to purify other things. It's used to purify drinking water. If you have a refrigerator that's got one of these removable cartridges, it says, change it in 3 to 6 months. One of the components in that is a layer of activated carbon that takes out off taste, it takes out any residual color, it takes out any residual pesticides or other things that might be in your water that you don't really want to drink. Activated carbon filters are used to take the mercury out of the exhaust from coal burning power plants. A lot of the foods that we eat that are white or colorless have been treated with activated carbon. If you can get packets of sugar in the raw, I think it's called, which is the way the first step in getting sugar in is kind of this brownish color. Well, the way they make it is it's then treated with activated carbon, so you get white table sugar. If you want colorless alcoholic beverages, you treat it with activated carbon, takes out all the color, so you get vodka. And it's used industrially and environmentally to clean up all kinds of things. Now, I hope you've all gotten a chance to see the coal if you haven't seen it before. Coal is essentially pure carbon, but it comes from plants. It comes from plants that lived millions of years ago. And if a plant dies and falls on the ground, it decays and you get a bunch of things, but it kind of goes away. If it falls into water, however, the layers of the plant can't fully decay, and so they pile up. And given millions of years, you can deposit other sediments, sand, erosion things, all kinds of other sediments pile up on the layer of compacted plants. And this puts them under pressure, and as they get closer to the center of the earth, the temperature goes up and they get hot. And so various kinds of chemical reactions can occur, and it causes reactions that cause rearrangement of the atoms to eliminate the things that are not carbon. So gradually you form a piece that's essentially pure carbon with sprinklings, tiny amounts of other elements left in it, and that's what we call coal. And we know that ancient people knew about coal because we've got coal carvings from about 4000 BCE. Gradually, coal replaced charcoal in smelting because people were cutting down and turning their forests into charcoal, and they were kind of running out, and they figured out that they could use coal instead. And since about the year 400, coal became the principal way to heat and cook in your home. But coal really got to be a big deal at the time of the Industrial Revolution, because the steam engine needs steam, and you get steam by heating water, which you get from burning things, and coal became the fuel of choice. And today we mine about 8 billion tons of coal a year that's mostly used in electrical generation plants. Just as you can take charcoal and make activated carbon, you can take coal and make a higher purity version called coke that's used in smelting today because it's purer than charcoal, and it's become the carbon material of choice in making steel. Petroleum is similar to coal in that it started out as some living thing millions of years ago, but this time, instead of plants, petroleum started out as algae and zooplankton that were living in the water, and they died, they fell to the bottom, they were covered by the water, so they didn't decay all that much, and sediments piled up. They found themselves under high pressure, higher temperatures. The atoms rearranged to leave a skeleton of essentially pure carbon, but these are smaller overall molecules than coal, so they're liquids, and that's petroleum. And there are surface flows. There's evidence that people knew about the surface flows of petroleum 4,000 years ago. If you go to Los Angeles, California, and go to the La Brea tar pits, you can see a surface flow of petroleum to this day. You can see it bubbling out of the ground. The first on-purpose wells were in China. The first one in the United States was in the 1800s. And petroleum, since it's a liquid, it's lots easier to do chemical reactions on it than it is a piece of coal. And so petroleum is the basis for making all kinds of chemicals, gasoline, jet fuel, asphalt, all kinds of other things come out of petroleum. But most of it is, in fact, like coal, burned. It's not used for other things. So that's the things that are essentially pure carbon, but carbon bonds with most of the other elements in the periodic table. So you get things like silicon carbide, which is a hard material used for abrasives. It's used as the piece that certain types of LEDs are made from, and you can make synthetic pieces of it that are beautiful gemstones called moissanite, and you can go to the jewelry store and you can buy beautiful moissanite rings as well. It reacts with carbon bonds to tungsten to make tungsten carbide for mainly cutting tools, but also turns out it's the little ball in a ballpoint pen, because it has to be really tough to maintain its roundness as you press on it and drop it on the floor and stuff. And so carbon can bond to lots of other elements in the periodic table as well. Carbon was the basis of smelting, but carbon can also bond with iron, and it's important in the structure of iron compounds. Back in the original process, there was very little carbon left in the structure, and it was a porous piece of iron with the impurities still left in it. And so then you had to call a blacksmith who could rot it. You heat it, you bang on it with a hammer, it flattens out the porosity and literally mechanically knocks out all the impurities as you fold it and bend it and hammer on it. And so that's how you get wrought iron. Gradually, people figured out they could leave a little more carbon to bond to the iron, and that would lower the melting point, so now the fire was hot enough to melt it, and now you could get an iron that you could pour, and that became cast iron. And you could make molds, you could make really complicated shapes. We still get cast iron pots and pans. The trouble with cast iron is that it's really brittle. And people also figured out how to control very precisely the amount of carbon left in the iron. And they developed a material called carbon steel that's got from 0.2 to 2% carbon left in the alloy, which makes it really strong. And people developed hotter furnaces so you can melt it and pour it into ingots and shapes. And it's got much better toughness and strength compared to wrought and cast iron. So now carbon can also bond to, since it can bond in so many ways to so many elements, a lot of them are in the category of what's called organic. It's called organic because the first ones were obtained from living materials. And they're mostly contained of, they mostly contain a short list of elements with smatterings of some of the other ones. And we've got a huge number of compounds that fall into this category that are really useful in our civilization as dyes and polymers and plastics and pharmaceuticals. And one can talk for hours and hours on each of these categories. But besides being the basis of materials that we use, carbon is the basis of materials that we are. Carbon is the basis of life on Earth because of its ability to make so many different kinds of structures. So carbon-based life has structures. It has carbon in ways that form structural materials that give the stalks to plants from the cellulose, the scaffolds for your bones, the tendons, all kinds of structural materials. It's the energy storage material for long-term storage in sugars and starch and fats. And in a molecule called ATP, I'll talk about in a couple minutes, that's a short-term energy storage material. Carbon is the basis of catalysts that allow cells to do chemistry better than any chemist living at room temperature in water, which is just an amazing feat. Carbon is the basis for information storage, electrical signal transfer, mechanical motion, and signaling within an organism and between organisms. And all of these things are because of the versatility of carbon-based structures. But carbon also powers our world. Sunlight is the main power source for the Earth. It heats the Earth, it provides power for ocean currents and weather patterns. And sunlight is also the basis for powering all living things by using an intermediary of a carbon compound. So this takes two reactions, basically. The first one is photosynthesis that captures the energy from sunlight and uses carbon dioxide and water and a whole bunch of chemical reactions that we still don't understand fully. It's really, really complicated how this occurs, but you end up making oxygen that's released back to the atmosphere that we need to breathe, and a lot of the energy in the sunlight is stored in a sugar called glucose. And this is the basis of the food web that supports all life on Earth. Because all of the organisms do another set of reactions called respiration. This is the chemical process for aerobic respiration because it uses oxygen. And this is what humans and lots of organisms use. There are some that put other things besides oxygen in this place. But it takes oxygen, carbon, and it releases carbon dioxide back to the atmosphere, water, and it makes this molecule I mentioned before, ATP, that's a short-term storage compound. This is just a schematic of cellular respiration. It's really complicated. And so all living things, humans included, are powered by carbon compounds from energy from the sun. But carbon also powers human civilization. Our power sources started out as human effort, gradually people learned to harness animals to help, and then water movement and air movement. Recently, there are other power sources here that humans use that are not carbon-based, but they're relatively new on the scene and we're under development. But for the most part, carbon compounds are still the dominant source of energy to run our civilization. And we do it by burning things. This is the equation for burning a candle. You take a carbon compound, react it with oxygen, gives carbon dioxide, water, and a whole bunch of heat and light, kind of uncontrolled. And people have learned to use that heat or the light to illuminate our world and to heat things and cook and generate electricity and power transportation and industry and you name it. Our civilization is powered by burning carbon compounds. So I hope that I've given you a good idea of what an amazing element carbon is and all of the things it has done for humans and human civilization through the years, and the fact that it is the fuel, the energy storage element for both life itself and for powering our world. But I'm going to leave you with some questions about what will the rest of the story be. Carbon was, the basis of how we got to where we are. But the question is, will it actually lead to our demise? Every day you get more reports of worrying trends that are based on the fact that we have a carbon-based world. There's changes in the climate, there's heat waves, floods, droughts, fires, pollution that's degrading our air, water, and soil. And the question is, will this lead to our demise or not? And counteracting that, every day you get new reports of things people are doing to mitigate these trends and adapt to their consequences. But the question is, will we be able to do this fast enough? And, I'm an optimist, and so I am quite hopeful that we will do this fast enough. However, I am reminded of Rachel Carson's warning. Rachel Carson wrote a book called Silent Spring that was published in 1962. I recommend that everyone either read it or reread it because it's as applicable today as it was when it was published. And one of the topics that she covers quite a lot in her book is how life forms adapt. And Rachel Carson leaves us with this warning that when life forms adapt, the essential ingredient is time. But in the modern world, there is no time. So, thank you.
Would you have your permission to put this on the web?
Sure.
Okay, thank you. Thanks, Dr. Davidson. Please come up to the microphone with your questions. As you're coming up, let me mention that this talk will be taped. It will be on our website in a couple of weeks. For people who are leaving Chautauqua, you can also send an email to us. The instructions are out there. Tell us that you want to be on our Zoom list. You can Zoom in and and listen to these talks. Also want to say that next week, Dr. Paul Farber will be talking about Silicon Valley and its successes and failures, comparing Apple with Theranos, whatever. Yeah, Theranos, thank you. And we've appreciated your attendance here, and we will now turn it back to questions. Bob.
Awesome talk.
Thank you.
What do you know about attempts to burn and heat and form carbon in space and then potentially somehow beam down to the surface of the earth the resulting energies or material. Is that completely ridiculous, or could we
Well-
see that later this century?
I don't know a lot about it. I know there have been experiments done to try and burn things in space. It's somewhat problematical because there's no gravity, so the combustion products don't leave, and it's got issues to burn something in space. And I think there are attempts to get other ways to try and beam energy back down from sunlight and stuff, but I don't really know where any of them stand. You never know what you'll get asked from this audience.
You said you were hopeful about the human race dealing with carbon and the blanket that we're creating and killing ourselves with. Could you give us some possible answers that wouldn't interfere with the lack of time, perhaps, that you mentioned? Are there ways that are being worked on that
Yeah.
you find helpful to solve this problem?
Yes, there are lots of ways. Countries around the globe are trying to switch to non-carbon-based energy sources. I saw an article just the other day that had a graph of how much solar power has been harnessed by various countries. The leader is China. They are also the leader in burning coal, but they seem to have a really good plan in place for using coal in the interim and getting enough other sources to get rid of the coal. We hope soon enough. The United States has, for a lot of years, been kind of against switching away from petroleum and coal, but even the United States is switching over fairly rapidly. There are processes that are beginning to be put in place on a large scale. They exist already on a small scale to capture carbon dioxide from concentrated sources like smelting, which liberates a lot of carbon dioxide, cement making, power generation, and while we're still burning coal and petroleum, capture it when it's concentrated and put it down deep in the earth. The hope is it will react with things down there and form the carbonates that was the form of the ores and things when we got them out, and put them in reservoirs that are impervious, and it'll stay put. So this is underway. People have mixed feelings about doing this, but in the short run, it's probably got to be part of the solution. So there are other developments well, those are the main ones that I know about, so I'll stop there. Thank you.
I think you already answered part of my question. My question involved a description of what's carbon capturing. And the second part of the question, do you see it as a viable alternative to help clean up the environment?
Is carbon capture viable?
Yes.
To help clean it up? I think it is to a certain extent. So you take this fairly concentrated stream that contains carbon dioxide, and by various ways of adsorbing it onto making it stick on something and then getting it back off in an even more concentrated form, or compressing it and to where it liquefies, you can separate it from the other gases in the stream, and then you put it into pipelines and they put it back down into depleted oil wells, for example, and other structures in the earth. Some people worry that unlike getting the petroleum out that was a liquid, putting this high-pressure gas back in, that it won't stay put. But there are other people that are quite sure that it will stay put, and so it is a growing thing that's being done. And in the short run especially, we have to do most anything we can to get rid of carbon dioxide. Oh, I forgot to mention, there's a lot of work being done to make things out of carbon dioxide. And so if you can capture it and then have it in a concentrated form where you can do chemical reactions on it, people are beginning to make plastics and some other things out of it. And the nice thing is that people are, when they develop new ways to make plastics, they're trying to make them so that they are degradable, so that that won't worsen our plastic problem.
Carbon is in the same family as silicon.
It is.
What is it about carbon and silicon that is different, that we don't have the just the plethora of carbon compounds that it would be silicon-based?
Okay. Silicon is, as he says, the element under carbon in the periodic table. So it's got 4 electrons, and you say, well, it should behave just like carbon. Only it doesn't. To the best of my knowledge, other than making a pure piece of silicon metal, or semi-metal, that's the basis for all your computer chips. Silicon doesn't bond to itself very well. And I can't think of any silicon-silicon bonded pieces that are like carbon-carbon bonded pieces. We use a lot of silicon as silicones, but the silicon isn't bonded to silicon. It's silicon, oxygen, silicon, oxygen, silicon, oxygen in all of the silicones. And it's a really useful, wonderful set of materials, but it's not like the carbon ones, because you can't bond the silicon to silicon. And if people say, well, why can't you have silicon-based life? Well, if you have carbon-based life, you've got glucose, you've got this long-term storage molecule, and when you react it, you get carbon dioxide, which is a gas, which is really easy to get out of a cell. It's a gas, it diffuses out, and away it goes. If you make a pure silicon oxygen compound, you get sand. SiO2 is sand, it's silica. And there are organisms that make it on purpose, and diatoms and certain other sea creatures and mollusks, they make silica on purpose for shells and structures, but to use it to power the life itself would be very problematical. And so in the, how many eons it's been that life's been developing, that route never has found a way to get started.
Doctor, I thoroughly enjoyed your presentation.
Thank you.
And I noted your degree of optimism that the human race will adapt. You also mentioned that carbon is the dominant source of energy currently. And as you probably know, and my background story is oil, as you probably know, the world is now using 102 million barrels of oil a day.
Yes.
A day.
A day, right.
The Minister of Energy for Saudi Arabia recently said oil or petroleum will be the dominant source of energy for the world until at least 2040. If that occurs, I think there's going to be a continuing rise in temperature, ocean levels, and so on. Can you just sort of say something to it? Thank you.
I closed with the quote from Rachel Carson, because I'm not sure we'll do it fast enough to avoid catastrophic things like fires and finding a diminishing place on Earth where people can live, and then there's going to be conflicts. And I try to be optimistic because I look at how fast the change to non-carbon sources is going, which is faster than people thought it was going to happen. And the things like carbon sequestration and making things out of carbon dioxide. And so I am hopeful, but Rachel Carson may have had it right, that we didn't leave enough time to get it done. We should have started on this when Jimmy Carter said that we should have a conservation effort and not use so much energy.
May I digress and just ask a short second question? I think nuclear energy is a solution. Do you?
I do. It has to be part of the solution because we can't get the others anywhere near quick enough. And they're not concentrated enough. You can get nuclear power in very small packages. There's a lot of work being done on small, tiny modular nuclear reactors that can be used in various kinds of places instead of having these huge monolithic things that if they have a problem, it's a really, really big problem. And there's work being done on using elements besides uranium to power it that are somewhat safer than uranium and all of its daughter products from fission. Who knows if fusion is going to ever happen? I don't know. It's been 5 years away for 50 years. So I don't know. But nuclear is going to have to be part of the solution, I think.
Dr. Davidson, I want to thank you on behalf of all of us for helping us look at science from a small element. And one of the things that we're learning every year is that science itself is a human activity. And it has to take place within the economy, within the polity, within society, and act over time. Right. And when you add all of those things, it's imperfect, but it's what we've got to work on these problems. Right. And we're going to keep doing it. And we appreciate everybody being here, making their contribution. And we'll be back next week, as Bob Spiritus said, looking at how one of the odd parts of Silicon Valley, is affecting what we do. And to help us do this so that we can have a minor fraction of the resources that the Apples and other people have, there's a basket on your way out. And at one time I asked people, I said, look, put a spare 100 in there. And amazingly, we got $200 bills that week. So it takes, your ones won't do it. But we appreciate your being here. Have another.
Yeah, great talk, really appreciate it. The slide on photosynthesis reminded me, the slide on photosynthesis that you talked about, about how that is a counterbalance to the carbon that we all produce. Is anybody working on artificial photosynthesis? Is that a viable solution as it consumes CO2 in the atmosphere to produce energy? Just curious.
I don't really know whether they are or not.
Yes,
that's a good question. Oh, the answer is yes?
Some, yeah.
Oh, can you elaborate?
It's not at a practical level, but they are working on techniques. Oh, yeah. Oh, you're right. Artificial photosynthesis is being experimented with. I wanted to make a comment with regard to Rachel Carson comment about time, but from the inverse direction. You have, in a healthy ecosystem, there's a balance between the photosynthesis and the respiration. Right. You make, you burn. Right. And respiration is just controlled burning. In fact, energetically, it's absolutely equal. If you dry out a piece of lettuce and burn it with a match, you get just the same amount of energy as if you respire it. Okay, so in effect, there was a period of time in the past when for millions of years, it was out of balance and there was a lot more food produced than could be eaten. So what, in effect, we are trying to do right now is eat 1 million a million years worth of food in 100 years, and it isn't working out.
Right, yes. I mean, what he points out is correct. If you looked at the equations I put, the one for combustion is exactly the same as the one for respiration, and you get the same amount of energy out, except that respiration does it in a way that it packages it up for later use, and it releases a little bit of heat. But when we burn something, there's no packaging for later. You just liberate it all now.
So things are bad, but actually they're getting a little better. According to the EPA, carbon monoxide has been reduced from 1980 to 2022 by 75%. Lead is down 99% because of the change in gasoline laws, no lead in cars, that's gone down. Nitrogen oxide's gone down 72%, and body. So many things are going in the right direction, okay? The trouble tends to be is there's still an awful lot of people who do not believe that we are contributing to the problem, that climate change is something that is a natural occurring event. So the other side of the coin is, how do you communicate to people who don't believe and still believe that the earth is flat?
Well, that's a really good question, and I'm not sure what the answer is, particularly because there are lots of wealthy, powerful interests that want to make sure people don't believe in a lot of this stuff. That's my opinion. Yeah, it takes time. Anything else?
Sorry. Question.
Could you come to the mic and speak up?
Sorry. A lot of industrial companies and stuff, especially in the United States, have, under regulations, been controlling their emissions and collecting the off gases or anything from manufacturing. Mm-hmm. Can you tell from your perspective how they have improved that collection mechanisms of collecting their off gases and stuff from manufacturing, and what they do with those then chemicals that and gases that they collect?
Okay.
And how that's used?
Your question gets a lot to this gentleman's comment about the reduction of carbon monoxide and NO2 and all that stuff. Now those regulations are for things that are classified as pollutants. There was an attempt to get CO2 classified as a pollutant and make industry start generating less and emitting less, but that fell by the wayside. Now, as far as the ones that are pollutants, they're captured oftentimes by absorbing them on activated carbon. Depending on what's, and changing the process to generate less of them in the future. When I worked at 3M, they had a pollution prevention pays program that did a whole lot to reduce and not make a lot of the pollutants that the company had been making. And so a lot of it is through not making it. And what you capture, what happens to that? That's a really good question. Some of the things that can be reused and have value are recovered and recycled. A lot of them are just buried, or some of them are then burned, which kind of just recycles the problem. Well, it doesn't. They don't let it get loose again, but it generates more CO2, but it decreases the volume, and then that's probably buried. There aren't really good solutions.
I can give them one. Don't be totally pessimistic, or we're screwed. Also, I grew up in Los Angeles in what was thought to be a golden age, could do whatever I wanted. Limits seemed for other people and other places, but when I would go out and play basketball or football in my yard, I couldn't breathe after 5 minutes, and I couldn't see the mountains, and it looked hopeless. But actually, government stepped in, and the air in Los Angeles is so much cleaner and clearer than it was when I was growing up. And that wasn't GM deciding to fix it by itself. That was government and people demanding it. So come back, we'll learn more next week, and it's up to us. So do it.
Thank you all.